So let's begin with the units and dimensions. So now, what do you mean by a quantity? So do you know about physical quantities? What is a quantity? Something is written on screen. So quantity is something which can be measured, right? It can be anything. The number of students in your class. It may be, uh, let's say, number of fruits. Okay, the number of 10 apples, you can say, or 15 bananas, etc., etc., or number of clothes in your wardrobe. Okay, so quantity is anything which can be measured. And what is a physical quantity? So physical quantity is quantity related to a physical system. Okay, so let's say it's a physical quantity, it's property of a material or a system which can be measured. Okay, for an example, you take me as a physical system. Okay, so my height can be a physical quantity. Okay, then my mass is another physical quantity. So the things related to a physical system which can be measured. All right, those are physical quantities. So why do you need to measure physical quantities? Why do you need to measure something? Any answer? Any guesses? Do you need to measure quantities? Yes or no?
Yes, sir. Yes,
Okay.
sir.
Why do you need to measure? Let's say I want to buy something. Okay, I want to buy sugar. All right, so I go to the grocery shop and I will ask for sugar. Okay, but I need to say I want this much amount of sugar, and for that measurement is required. Okay, right? Then another example, let's say I want to purchase a t-shirt for me. Okay, so now here also measurement is required, right? Because any t-shirt will not fit me. So measurement is required. How much is my shoulder and everything? Okay, so according to that we have small, large, XL, etc., etc. So measurement is required in our day-to-day life. Okay, for many things,
Yes, sir.
various things. Okay, without measurements nothing is possible. Our life is impossible, right? So to measure any quantity we need some standard, and that standard is known as a unit. Okay, so what is a unit? Unit is a reference standard for a measurement. Okay, so for an example, how do you measure height? if i ask if I ask you to measure my height, how will you measure?
Centimeter.
Okay, but yes, Sharda.
So meter,
Okay, but
centimeters.
you will take some tape, no? Right, there will be some markings. Okay, meters, centimeters, meters, there will be some markings. So you need some reference. Okay, let's say I build my reference, my pen, let's say. Okay, so if I keep how many 35 pens one on top of each other, no, 35 will be too much. Let's say 22 pens or something. If I keep one on top of each other, it is equal to my height. All right, so then the length of this pen becomes the unit. That's a standard I'm using for measuring my height. Okay, but this is not internationally accepted standard. Okay, so internationally accepted standards are known as the units which are recognized internationally. Okay, so this is unit. I can use this unit for myself, but I cannot say the my height is equal to 22 pens. Okay, because everybody else in the world doesn't have this pen. right? Maybe few people have.
Yes, sir.
Okay, so what is unit? It is arbitrarily chosen and it's internationally accepted reference standard for a measurement. Okay, and for length we know it's a meter. Then what are the requirements of this reference standard? So it should be invariable with respect to place and time. Okay, so let's say I measure my length here and I go somewhere else. Let's say I come to Chennai and measure my length. Okay, so I use a tape over here and I use another tape in Chennai. So it should give me same reading, right? So it should be invariable with respect to the place and time. Then it should be easily available and reproducible. So these are the requirements of a standard. Okay, so now I'm sorry. So these are the requirements of a standard. So now earlier in physics we used to study motion only. Okay, we meaning in 17th century, 18th century, people used to study only the motion. And what are the quantities which are important for motion? Those are length, mass, and time. Okay, so if you think about the mechanics, the study of motion, if you know about length, mass, and time, if you know their units, then all the other physical quantities that come in mechanics, those units, their units, you can figure out. Okay, so from the unit of length, mass, and time, different different parts of the world, they had different systems of units. Okay, so those systems were FPS, CGS, and MKS. So what is FPS? It is foot pound second. So unit of length in this FPF system, FPS system is foot. Unit of mass is pound, and unit of time is second. Then the other system was CGS. The unit of length is centimeter, unit of mass is gram, and unit of time is second. And there is another system which is known as MKS. So here the unit of length is meter, unit of mass is kilogram, and unit of time is second. Okay, so this is simple.
Yes, sir.
Okay, so different people all over the world. So whatever was convenient to them, so they devised unit according to that. Okay, so there is one example. This is a famous story. So how is unit of length foot? Okay, how that came into place? So there lived a king somewhere, and he said one day the unit of length in our country, okay, or in my kingdom is going to be length of my foot. All right, and next day onwards, the unit of length there, it was foot. Okay, which was length of the foot of that king. All right, so nowadays we don't have such a freedom. So, uh,
Sir, is this real story?
is this real? I read it in some book.
Okay, sir. Okay.
Okay, but I read it in physics book, nowhere else. So most probably it is a real story.
Okay, sir.
Okay, but see, yeah, length of my foot is little lesser than foot. Okay, so maybe the people were tall in those times. Anyways, so this is clear. I don't think there would be any problem in this one. All right. So now physical quantities can be categorized into two types. So one type is of fundamental quantities. They are also known as base quantities, and the other type is of derived quantities. Okay. So what are fundamental quantities? So we took these three examples, right? Length, mass, time. So those are quantities which are required for finding out the units of all other quantities. And how do we find units of these quantities? Let's say length, mass, time. So we actually measure them. Okay, we actually measure them. So the quantity is defined through a measurement process for a system of units is known as fundamental quantities. Okay, so in these three systems of units, length, mass, and time were chosen as the fundamental quantities because these quantities if you know the units of these quantities, you can make units of all other physical quantities in mechanics. Okay, and only the mechanics was studied in those times, right? But now you can make one system of unit where you say that force is my fundamental quantity. Okay, so you throw away mass and you pick force, let's say force, then length and time as your fundamental quantity. Okay, so still you will be able to make the quantities of all other physical quantities in mechanics. All right, so if you define a system of units, you need to define some quantities, okay, by measurement, and those quantities are known as what? Fundamental quantities. Then all other physical quantities, they are known as derived quantities. Okay, so for fundamental quantities, you will define their units using the measurement. You will actually measure them. And what are derived quantities? So derived quantities are those whose units depend upon the fundamental quantities. Okay, so these are the quantities which depend on the fundamental quantities for their measurement. Okay, so they are expressed in terms of the fundamental quantities. And if you take SI system, okay, I didn't define SI system yet, but if you take SI system where length, mass, time, these are three of the fundamental quantities, then you can find units of kinetic energy, force, momentum, etc., etc. Okay, so these are derived quantity, right? Got it? Fundamental and derived.
Yes, sir.
Okay, so what is SI system? So this is international system of units. So earlier we saw that there were three fundamental quantities only, three base quantities. Okay, because earlier we used to study only mechanics, but now we have got thermodynamics, okay, then electrodynamics, then modern physics is there. So now the number of quantities have increased, and to define the units for all these quantities, now there are thousands of quantities. So to define units for all these quantities, we need some more quantities. Okay, so length, mass, time are there. These are the basic fundamental quantities, and in addition to that, we need electric current, then temperature, then amount of substance, and luminous intensity. These are some more fundamental quantities. So now we have an international system of units where we have got seven fundamental quantities, and there are two supplementary quantities too. So what are these seven fundamental quantities? Length, mass, time, electric current, temperature, amount of substance, and luminous intensity. Okay, and their units are kilogram for mass, then meter for the length, second for time, then ampere for electric current, then Kelvin for the temperature, and for amount of substance it is mole, and then for luminous intensity it is candela. Okay, so out of these, we'll stick with length, mass, and time for the mechanics. Okay, because for next few days we are going to study mechanics only. All right, but for this chapter, we need to know units of all physical quantities. All right, so there are two supplementary quantities too. So is there any question in this? Fundamental quantities?
No, sir.
No, Sarda?
No, sir.
Okay. So there are two supplementary quantities too, and they are plane angle, and the second one is solid angle. Okay, so what do you mean by a plane angle? So do you know? Yes or no?
No, sir. Its unit is radian, I think, but I don't know plane.
Okay. So plane angle is an angle which we can draw on a plane. Okay, so our day-to-day angle, the angle we know about is the plane angle. Okay, so what is a plane angle? So let's say we draw a circle, Okay, and then we consider some arc over that circle. Let's say we consider this arc AB over the center, sorry, over the circle, and the angle subtended by this arc at the center of the circle, it is known as the plane angle. Okay, it is angle between two rays, any two rays. Okay, even if you don't define a circle, you take two lines, then if they are intersecting, the angle between those two lines is a plane angle. All right, so let's call it theta. And how do we find this angle? So in SI system, we define angle as arc length upon radius. Arc length divided by the radius. So theta equals to length of this arc, let's call it L, divided by radius, which is R. Okay, and what is unit of this? The unit is radians. Okay, so let's say angle is equal to 1 radian. What does that mean? It is length of the arc divided by radius. And if it is equal to 1, that means length of the arc is equal to what? It's equal to length of radius. Alright, so radian means in terms of radius. Okay, this is clear?
Yes, sir.
Okay, so now what can be the maximum angle which you can make, okay, on this circle?
360 degree.
360 degrees. Okay, so what is the maximum angle in radians?
2 pi radian.
Will be 2 pi radian. Okay, so maximum angle over a circle, let's say I start from this point and I come back at this point. Of course, I can perform n number of rotations, but I'm not considering that. Okay, in one rotation, let's say I start from here and I come back over here. So how much of angle do I cover? How much of angle is subtended by that arc at the center of the circle? So it is 2 pi radians. How? So let's see. So angle, let me call it theta max. So it is equal to what? If I cover a complete revolution on this circle, then the arc length will be equal to the circumference of the circle,
Circumference.
and we have radius in denominator. So it is equal to 2 pi r divided by r. So it's equal to 2 pi radian. You can write r radian in short. Okay. So this is maximum angle that can be subtended at the center of the circle. Okay, and it is subtended by what? It is subtended by the arc length, which is equal to what? Circumference of the circle. Okay,
Okay, sir.
all right. So then next, let's see the conversion factor between degrees and radians. Okay, so we already saw this, but let's revise it. So what is the conversion factor between degrees and radians? So how much is this angle over the circle in degrees?
360 degree.
360 degrees. Okay, so I can say 360 degrees is equal to 2 pi radians, and therefore 1 degree is equal to 2 pi divided by 360 radians. Okay, or I can cancel out this 2, so I can divide by 2, so I get pi divided by 180. So it is pi divided by 180 radians. And similarly, if I want a radian in terms of degrees, then what should I do? So 1 radian is equal to, then I will take 2 pi on the other side. So it is 360 divided by 2 pi, or 180 by pi. So it is 180 divided by pi in degrees. Okay, so if you want to convert radians from degrees, radians to degrees or degrees to radians, you should use these two formulae. So 1 degree equals to 2 pi by 360 radians, and 1 radian equals to 180 by pi. Okay, degrees. So this is clear.
Yes, sir.
So this is one supplementary quantity, the angle, plane angle. And there is another one. So let me add a page over here. So the another supplementary quantity is known as solid angle. Okay, so in short, I can say the plane angle is two-dimensional angle and solid angle is a three-dimensional angle. Let's see how. So to define plane angle, I consider which thing? I consider a circle. Okay. So to define solid angle, I consider a sphere. So let's consider a sphere. Now I cannot draw it. Okay. I mean, you won't find any difference between circle and sphere in this diagram. Okay, because this is 2D paper or 2D tab over which I'm drawing it. But imagine it's a sphere. Okay. So it's a ball. Now, if you consider some area on the sphere, let's say I consider this much area. Okay. And if I join each and every point at the boundary of this area to the center of the sphere, I join each and every point like this. Okay. So what will I get? So I have joined 4 points only, but let's say I join each and every point. What do I get? I will get a cone. Yes or no?
Yes, sir.
Okay. So if I join all points like this to the center of the sphere, I will get a cone, and that cone is called as the solid angle. Okay. So this cone is known as the solid angle. So let's denote it by d omega. Okay. So d omega is my solid angle, and it is subtended by this area at the center of the sphere. Okay. So now how do we define this solid angle? So solid angle is defined as area divided by r square. Okay. So what is r? R is the radius of the sphere. Got it?
Yes, sir.
And the unit of the solid angle, it is t radian.
Sir, why we putting that omega, sir? Like, I don't
Mhm.
understand why. It,
I'm calling this cone as d omega. Okay, I have to name it
so,
something, no?
that. Okay, sir. Okay,
Yeah.
sir.
So I'm calling it d omega, right? You can use any letter, doesn't matter. Then this is how I define solid angle. Now let's say I want to find out maximum possible solid angle. How much would be that? So maximum possible, just like we found maximum plane angle. So maximum value of solid angle. Okay, which can be subtended at the center of a sphere. It's simple, no? See, now how do you define this solid angle? It is this area divided by r square. So how much is the maximum possible area? It is the total surface area of the sphere, right? So maximum solid angle defined by, subtended by the sphere at the center would be the surface area of sphere itself divided by r square. Okay, you can't get more area than the area of sphere itself. Yes, no?
Yes, sir.
Okay, so let's call it omega, sorry, let's call it omega max. So it's equal to area of sphere divided by r square. Okay, so it is 4 pi r square divided by r square. So r square and r square gets cancelled out. So you get 4 pi st radian. Alright, so this is how we define solid angle and this is how we find it. Okay, so right now I am defining it in simplest possible way, but we'll see in electrodynamics, that is in electrostatic, in Gauss's law, that how to define solid angle in proper way. Okay, right now I have just defined it in a particular context. Okay, so there we'll see general solid angle. All right,
Okay, sir.
any questions till now?
No, sir.
No, sir.
Okay, so then next, as I said, these are what the fundamental quantities. We have got 7 fundamental quantities and 2 supplementary quantities. So if we know units of these quantities, then we can find out units of all other physical quantities. Okay, so there are thousands of other physical quantities and we can find out units of all of them, provided that we know the formula which connects those physical quantities and these fundamental quantities. Okay, and we know the units of fundamental quantities. All right, so let's see some examples. For an example, I want to find out unit of area. What's unit of area?
Meter square.
Meter square. So I know the formula. Let's say I have area of a rectangle. So it is length into breadth. Okay. So unit of length is meter. Unit of breadth is also meter. So it is meter square. Right. I want to find unit of the volume. What is that?
Meter cube.
Meter cube. Okay. Let's say I take a cuboid. So its volume is length multiplied by breadth multiplied by height. Okay, LBH. So its unit is meter cube. Okay. Then for an example, let's say I take force. Okay. Before that, let's consider velocity. Okay. What is velocity? It is displacement.
Meter per second.
Yeah. It is displacement or time. Okay. So unit will be meter per second. All right. So provided we know the formula, we can find out the units. Okay, so these are very simple cases. Even if, so there will be some complicated cases also, but if we know the formula, we can find out units. Okay, there is no issue. So now there is a relation between the derived quantities and fundamental quantities. Okay, and that relation is known as dimensions. Okay, so the way in which the derived quantities are related to fundamental quantities, so that relation is known as dimensions. Okay, so the textbook definition is the dimensions of physical quantity, they are the powers to which the base quantities of fundamental quantities are raised to get the derived quantity, that particular quantity. Okay, so how do we represent dimensions? So let's say I want to find out dimensions of area. Okay, so for an example, I want to find out dimensions of area. So I will write area like this. I will put it in a box. Okay, and what is dimension? It is the power to which fundamental quantities are raised in order to get the representation or the formula for this particular quantity. Okay, so what fundamental quantities are required to represent area?
Length.
I need only length. Okay, so it is length multiplied by breadth, or I can say it is length multiplied by length itself. Okay, it is L to the power 2, right? What are dimensions of volume?
L cube.
L cube. It is length to the power 3. Then I want to find out dimensions of velocity. So what are dimensions?
L t power minus 1.
Yes, it is displacement upon time. So it depends on length. So in numerator I have L to the power 1. In denominator I have t to the power 1. Okay. Dimension of length is L raised to 1. Dimensions of this time is t raised to 1. So I have L raised to 1 divided by t raised to 1. So if I take this t raised to 1 into numerator, it becomes t raised to minus 1. So dimensions of velocity are L raised to 1, t raised to minus 1. Okay. Similarly, let's find out dimensions of acceleration. So let's put acceleration in a box. What is acceleration? It is
L t
change.
power minus 2.
Yeah. What is the formula? V minus u divided by t. Final velocity minus initial velocity divided by time. Okay. So now here we understand one thing. So in numerator, I have subtraction of two similar quantities, similar physical quantities. Okay. So this numerator will have same dimensions. Okay, these two quantities have same dimensions, and if I subtract these two quantities, dimensions don't get cancelled out. Okay, so this is change in velocity. It will have dimensions same as that of velocity. Okay, so what are the dimensions? L1. Okay, so I need to put this in box 2. So it is L1 t raised to minus 1. We just found dimensions of velocity, and in denominator I have t raised to 1. So if I take that into the numerator, it becomes t raised to minus 1. So I have L raised to 1, t raised to minus 1, that is t raised to minus 2. So L1 t raised to minus 2. Then next, I want dimensions of force. So what are dimensions of force? So force can be represented
Mass
as,
into acceleration.
yeah, it is mass into acceleration. So dimensions of force are equal to dimensions of mass multiplied by dimensions of acceleration. So it is m raised to 1, and dimensions of acceleration are L1 m1 t raised to, sorry, L1 and t raised to minus 2. So dimensions of force, okay, they are L1 m1 t raised to minus 2. And I want one more, that is energy, or you can say work. So what is work or energy? It is force multiplied by, work done is force multiplied by
Displacement.
displacement, right? It is force multiplied by displacement. So dimensions of work are equal to dimensions of force multiplied by dimensions of displacement. So that is L1 m1 t raised to minus 2 multiplied by dimensions of displacement are L raised to 1. So the dimensions of work are L2 m1 t raised to minus 2, right? Okay, so is there a question till now? Any question?
No, sir. No, sir.
Okay,
No, sir.
so if we know these many dimensions, we need to know dimensions of area, volume, then we need to know dimensions of velocity, okay, force, then energy and acceleration. And if we know the formula which connects these quantities with another physical quantities, another physical quantity whose dimensions you want to find, then if you know the formula, you will be able to find out the dimensions of that physical quantity. Okay, so there are thousands of other physical quantities, but what do you need to know is the dimensions of these quantities. These should be by heart, and the formula connecting these quantities with any other physical quantity. Okay, then you will be able to find out dimensions of that quantity. Okay, so you don't need to by heart dimensions of all physics quantities over there, right? But you need to know the formula. So for an example, let's take an example. So for an example, I want to find out dimensions of the universal gravitational constant. Okay, dimensions of G. G is the universal gravitational constant. So now, who knows the formula for this?
F is equal to G M1 M2 by R square.
G m1 m2 or R square,
R
distance
square.
square. Okay. So what is the formula? Where does this quantity show up? So if we have two masses, m1 and m2, and we know the Newton's law of gravity. Okay, every mass in the universe attracts every other mass with a force which is directly proportional to product of their masses and inversely proportional to the square of distance between them. Okay, so let's say distance between two is r. So the force of attraction, gravitational force of attraction between these two masses is given by g multiplied by m1 m2 over r square. And now the question is to find out dimensions of G. So see, I know the formula which connects force with G. Okay, so I can find out dimensions of G. Very simple. So I want dimensions of G. So I will take all other terms on the other side. So I can write G equals to F divided by what? I can take R square on this side. So it is FR square divided by M1 M2. Okay, because m1 m2 is in multiplication. If I take it on other side, it goes into the denominator, and r square is in denominator. If I take it on other side, it will go to numerator. So fr square divided by m1 m2, that's equal to dimensions of G I want. So it's equal to dimensions of force multiplied by dimensions of r squared, dimensions of m1, dimensions of m2. So that is L1 M1 t raised to minus 2. Then I have R, which is length. So dimensions are L raised to 1. I have to take square of that. And then I have M1 M2 in denominator. These are masses. So M raised to 1, M raised to 1. Okay. And then let's take it. Okay. So it is M raised to 1, M raised to 1. I can cancel out this M raised to 1 from numerator, and then I will take this m raised to 1 to the numerator. It becomes m raised to minus 1. So in numerator I will have m raised to minus 1. After that it is L raised to 1 square. Okay, that is L raised to 2, and again I have L raised to 1, so it is L raised to 1 plus 2, that is L raised to 3. So it's L raised to 3, m raised to minus 1, and t raised to minus 2. These are dimensions of universal gravitational constant, if my algebra is correct. Okay, so please check my
Yes, sir.
algebra. Right, if calculations
Correct,
are
sir.
correct, then these are the dimensions of universal gravitational constant. If they are not correct, then it's wrong. Okay, so got this? How to find out dimensions?
Yes, sir.
Yes, sir.
Okay, so then let's see some multiple choice questions because we are studying for NEET. Okay, so let's see this question. Which of the following pairs of physical quantities does not have same dimensional formula? So here questions can come from all across the 11th and 12th standard, right? They can take formulae from all of your 11th standard and 12th standard, and they can form questions based upon dimensions of all those quantities. Okay, so knowing the formula is must here. Okay, so can you tell the answer? Which of the following pairs of physical quantities does not have same dimensional formula? Okay, work and torque. So we know what is work. Work is force multiplied by displacement. And what is torque? Torque is moment of force. Okay, so it is R cross F, right? If you know, it's okay. Don't know, we are going to see that. Okay, afterwards in rotational motion. Okay, so this is the formula. So it is force into length. Basically, work is also force into length, and this is also force into length. So they have same dimensions. The next is angular momentum and Planck's constant. These two also have same dimensions. Okay, so what is angular momentum? Angular momentum is moment of linear momentum. So moment meaning is r multiplied by linear momentum. Okay, r cross p. The dimensions are L1 and dimensions of momentum. What is momentum? It is mass into velocity. Okay, so it is r mass into velocity. So L1 m1 and the dimensions of velocity are L1 t raised to minus 1. So dimensions of this one are L raised to 2, m raised to 1, t raised to minus 1. And the Planck's constant. Okay, so do you know the formula which has Planck's constant in it?
E is equal to h nu.
E equals to h nu. Okay, so we got dimensions of angular momentum. They are L2 m1 t raised to minus 1, and we know E equals to h nu. Okay, nu is frequency, right? So you can write it as 1 over t. Okay, so E equals to h upon t, you can say. So if you take t on the other side, you get h equals to et. What are dimensions of E? We just found L2 m1 t raised
M
to
t power minus 2.
t to the power minus 2, and here we have t raised to 1. Okay, t means t raised to 1, right? So we have t raised to minus 2 plus 1, that is t raised to minus 1. So we have got L2 m1 t raised to minus 1. Okay, so angular momentum has dimensions of L2 m1 t raised to minus 1. This one also has same dimensions. So not this one also. This one has first pair has same dimensions, second pair has same dimensions. Third one is tension and surface tension. Okay, so tension is force. You know this tension in the string. Tension is force. Okay, but how do we define surface tension? So surface tension is force acting per unit length of a liquid surface, free liquid surface. Okay, so definitely one is force, the other one is force upon length. So they can't have same dimensions, they can't have same units. So this is the answer. And last one we don't need to check. Okay, so it's impulse and linear momentum, they have same dimensions. So got this?
Yes, sir.
Yes, no, Sharda?
Yes, sir.
Okay, good. So let's move on to next question. Okay, by the way, in this chapter's homework, so I have given lots of dimensions to find out. Okay, so it will be a lot of work. Okay, and after that, I am still making the multiple choice questions, but I will upload it and you can keep finding it out. Okay, find out dimensions and you can do it over this entire week. All right. till the time we finish this chapter.
Okay, sir. Okay, sir.
Along with the other homework. Okay. So the dimensional formula for Planck's constant we just found out. What is that? L2 m1 t raised to this one, no? T raised to minus 1. L2
Yes,
m1
sir.
t raised to minus 1.
Option B.
Option B. L2 m1 t
B.
raised to minus 1. Right. Next one. Dimensions of kinetic energy is same as that of which of these?
Work.
Okay, work. This simple one. I don't think, okay, they will come to this level. Anyways, next question. The ratio of dimensions of Planck's constant and moment of inertia has dimensions of. Okay, we found dimensions of Planck's constant. They are L2 m1 t raised to minus 1, right? L2 m1 t raised
Yes,
to minus
sir.
1. Yeah, I don't memorize these. Okay, and then moment of inertia. So what is moment of inertia?
mr square.
Mr square.
I is equal to mr square.
Yeah, I equals to mr square. So m1 r raised to 2 meaning L raised to 2.
L square.
Okay, so this thing gets cancelled out.
Frequency.
Yes, t raised to minus 1. Okay, inverse of time, that is frequency. Okay, this one. The expression for Boyle's law, the product of PV has dimensions of. Yes, force, energy, impulse, momentum. You know this or don't know? It's energy.
I think energy.
Okay,
Energy.
or we can find it out. It's energy. See, pressure multiplied by volume. Okay, so pressure is force upon area, volume is volume. Okay, so dimensions are force L cube divided by L square. So let's cancel this out, right? We'll have L in the numerator, so it is force multiplied by length, that is force multiplied by displacement, you can say. So it is work. Okay, so which has same dimensions as that of energy. So this is the answer. Simple.
Yes, sir.
Okay, and that's it for today. Okay,